All right, let's see. Next, applied optimization problem. This is more mathematical, uh, but it's good practice just for working with a graph. And so the idea here is going to be that we have a region in the xy plane that is bounded by the x-axis and the function 25 minus x squared. This is activity, I should have started with this. This is activity 3.4 by 4. 25 minus x squared is my function. So just to draw a quick sketch of that. Right. So this is 25 minus x squared. Good. Now construct a rectangle whose base lies on the x-axis and is centered at the origin, and whose sides extend vertically until they intersect the curve 25 minus x squared. Let's see, draw it with a different picture here. So my rectangle is centered at the origin, and the top is going to be formed by the rectangle. So I go out to here and I go up to there. So notice when I do that, right, I can call this point x comma y, where x now is just this length, right, from here to here, and then y would just be the height from there to there. Okay, and so then overall then you'd have another x over here, and so if you want the full area of our rectangle, the full area is going to be 2 times x, right, or x plus x times y, so 2x times y. Okay, now the way we set this up, right, the y is actually coming from a function, and so you can replace the y here with the function name. So this is going to be 2x times 25 minus x squared. Good. And now we can do our usual routine. Let me check this real quick. The focus looks a little off. Is it back on? I probably just made it worse, didn't I? I keep doing this for each video. Okay. Now, since we're going to be differentiating this, it's probably easier to just rewrite that. So 2 times 25, 50 times x minus 2 times x cubed. Good. And so now we're going to try to find the minimum value of this function. Is it the minimum or the maximum? Which such rectangle has the maximum possible area? So we want to maximize that. Okay. Any restrictions on x? You can kind of look here. Well, x go from anywhere from 0 out to this point right here. What is this point right here? This is where the 25 minus x squared would be 0. So that point is where 25 minus x squared equals 0. Or you could solve that, x equals 5. So it looks like our values here are that x must be bigger than or equal to 0, less than or equal to 5. Good. And now, of course, we're in a we have a continuous function on a closed interval, so we will use the closed interval method. Okay, and so we'll build our table. I've got 0 and 5, and the last thing that's remaining here is I need the critical points. So I don't really need to do everything in red here. Maybe I'll do some blue. So let's do the critical point in blue. 50 minus 6x squared. Okay, set that equal to 0, and x is equal to plus or minus the square root. Square root of 50 over 6. Sorry, that's the trouble with using these thick pens. They show up better on the screen, but they're harder to read. So that's approximately 2.886. Okay, now the problem with using this is that we have both the plus and the minus, but we're in the interval from 0 to 5, so we can get rid of the negative one and just use the positive. And so we'll put a 2.88 here, 2.886. Now if I put 0 into my formula, right, I get a 0 volume, or area, sorry. And then if I put 5 into my volume, I keep saying volume area formula, I also get 0. And so really, anything that you get from 2.886 is going to give you your max. So the maximum comes with this value of x. Okay. Let me pause a second and I will compute that for you. Alright, so if I actually make that computation there, I get that the area is, well, it's 500 divided by 9 times the square root of 3, or approximately 96.225. Okay, so that's the value that goes in here. Good, so that is the global maximum of our area, and that's using the length of the side here is 2.886, or square root of 50 over 6. Very good.